So in this lab, we're just going to call this a simple traverse. 3 points is a little bit too simple. 4 points, I believe, is a good basis. Most any property will be four-sided at least, even though we can have all kinds of different sizes. And I've kind of nicknamed this how to make coordinates. Now, if you have any surveying experience, you understand that you see coordinates and coordinate values for the points that you're occupying, backsiding, staking out, observing, etc. How does that come to be? Well, this is where we begin to explore the secret sauce and see how the magic is made. Before we go further, I want to point out, as several people may point out, that if you have surveying experience, you may snicker at the level of simplicity of this lab exercise. Understand, again, this goes back to my philosophy of it's better to understand what happens when you mash the button than to know which button to mash. Now, what I mean this in specifically, besides it being simple four-sided, for the lab exercise, we will be simply turning one horizontal angle right. We'll backside a rod, we will foreside a rod. This is by far not the most precise way to do a survey. Yes, the equipment will produce a much more precise survey if you use a bipod to brace the rods, if you set a tripod up with fixed targets. You'll especially increase the precision with redundant angles, whether if they are doubled or direct and reverse. But those things we know are out there. We want to have some error to reduce and process and account for and adjust, but also I'm trying to make this simple because at the end of the day, whatever you turn the angles from, fixed backsides, if you turn 4 sets of angles, if you turn 3 sets inside, 3 sets outside, whatever, you're still coming up with a horizontal angle. And so we're just going to keep it simple so that it keeps flowing in the field and so that we have less data to process. So what you may not appreciate is, let's say you're doing besides the extra time in setting up bipods and tripods, obviously it's quicker just to take a backside on a rod and then turn a foreside to another rod. But if you're doubling angles or turning direct and reverse, then or if you're wrapping a set, then you have to do some computations to figure out what your mean horizontal angle is at each station. So by just observing one, we're greatly simplifying your assignment and making it more easy to digest. Just understand that multiple observations produce better means that are a more probable value of the real thing, but we're not going there this time. All right, as I have said before on many occasions, field notes are the preference of who's taking them. Everybody has a different format. The main thing is make sure that you can read them. They need to be legible. Your 4s and your 9s and your 7s and your 8s all need to be clearly distinguished. When you write in a hurry and use improper lettering techniques, some of those numbers can look like the other numbers and create errors that you can't chase down. So keep track of your lettering. Make sure that your numbers are legible. The format that I've used is just the simple one that I learned. Station also has some other information underneath it. Horizontal angle is basically your next 2 columns. Slope distance, and then zenith angle. Now, I've saw people try to cram all the angle into one of these lines and get rod heights and descriptions. Typically, we'd put the rod height out here in the station because you've got room for it, and your descriptions go over here on the right hand side of the page where all of your elaboration goes as well. So follow me on this. The format that I've typically used, we start on 2 and backside 1. we're numbering, we're just assigning numbers to where we're setting up the instruments. You would think call it 2, call it 1, and set it from there, and then your 2. The problem with that is if you don't know how many points it's going to take to get around it, then you don't know what to call that last number. So by calling it 1, that's really where your traverse starts in a way, anyway. That keeps things simple. You never go wrong with 2 backsighting 1 and then 3. Now, if we had other side shots, I would say start them at like 20 or 10 or 50. You leave a gap in there for additional control that you might need later. Now, again, we were not doing any side shots in this exercise, just simple traverse basics. The side shots will come in the next lab for the topo. So, a little bit of nuance. Follow me on this. Our HI, well, back up. Before we get into horizontal angles and slope distances, we add a header. Instrument at 2. This is the instrument symbol. That is not a very good one, but that is an at symbol. At 2. Instrument at 2. Backsighting 1. And somewhere in this first setup, in the old days, or if all you're going is magnetic, you take a magnetic observation, and you find that 2 backsighting 1 is south 5 degrees west. Now I'm going to go ahead and skip over here to the sketch. Notice here's 2 in the northeast corner of the traverse, and we're backsighting 1 down here, and that's a south 5 degrees west magnetic. So that's where we are so far in the notes. Now we're going to level up. We're going to observe the rod on the backside, and we're going to zero set. This is where we're going to electronically tell the instrument this angle is 0, and it will go to all zeros, and all of your horizontal angles will be referenced from your backside. We're taking a backside distance and a zenith angle here for a unique reason that's maybe not necessary, but if we were doing this as an actual traverse in application, this would be like 30, 40 years ago when single turn angles and azimuths were and field books were the norm, which they're not now. You would go ahead and take a backside distance, which is no good without a zenith angle, so that when you got back around and you set on 1 and you foresight 2, you would be able to tell if something had been moved. And sometimes we would cover up traverse nails so that people would not vandalize them or pull them up. And sometimes we would need to know the distance to stake out to find number 1. You could figure out the angle to turn just by going ahead and running up your angular closure beforehand. But this backside distance gave you what you needed to be able to find number 2 when you came back to number 1, and realize this wasn't just a 90-minute lab exercise. It could take days to survey a piece of property and come back to 1 and 2. Or you might get started and then it might rain, you might go on vacation, you might have to go work on other jobs, it might be a while before you came back. So this way you always had a distance reflected back on 1. For this exercise, we are not averaging 2 backsighting 1 with 1 foresighting 2. This is just here for informational. So we enter this data over here. The HI is 488. That's something we'd measure with the pocket tape to the middle of the instrument from the nail or the pin, monument, whatever we're occupying. And the rod height is 5.02. And unless it's changed, we're going to assume that the rod height remains a constant 5.02. When you're having to raise or lower or use 2 different rods, you'll have a rod height entry at every shot. But if not, you assume that the last rod height entered is the same rod height going forward, and that's also how your software is set up. So we go to number 3, we turn a horizontal angle of 79.54.50, measure slope distance 137.10, and a zenith angle of 89.45.35. Then we'll move ahead. So now we've located this number 3, which is a nail. So we're on a rebar, backside a rebar and cap. Foresight number 3 is a nail. Now in a way, we're already 3/4 of the way done, but we're really only 1/4 of the way done. We could establish preliminary coordinates on these 3 points, 3 out of 4, but we're only 1/4 of the way done because we've only made 1 of the 4 observations. Next, we'll move up, instrument at 3, backsighting 2. We get a new HI because the instrument height changes every time. And even though I've used capital H, capital I in the leveling or trig leveling world, this could be a lowercase HI or what's known as the plus up, the elevation that you're plussing up from, or the difference in elevation that you're plussing up with the pocket tape from down below. Simple horizontal angle 89, 49, 21, 174, 73, 91, 12, 45 gets us back to number 4. Now you could say, well, we're done. That's a concrete monument. We got coordinates on all 4 points, but we don't know how good these measurements are. We don't know but what there's a blunder or that there's something going on until we complete the traverse, which obviously I'll skip through it, but we move up on 4, get a new HI. I record the horizontal angle every time as 0 because that helps you remember to 0 set. You might not remember to 0 set, or you might 0 set and then do something else and your 0 is off. You know, a good practice for precise surveying is not only zeroing, collecting it, but also when you're through, even after, if you turn your forward traverse leg first and then take a lot of side shots, you take another backside observation to make sure that your angles are not off. And then we move up on 4, get a new HI, move up on 1, backside 4 with 0. We turn to number 2, our starting point, horizontal angle 76, 40, 12, and here's where we are. Now, let's talk about this sketch. I packed a little bit of information into this sketch. So we know that we're starting at 2. So our back azimuth, being south 5 degrees west even, is 185.00. That's our back azimuth. We're going to be traversing this way. So our azimuth is actually a 5. We'll use that, and first thing we're going to do, this is just putting it all in perspective. We add up all these horizontal angles. They sum to 360, 0021. We come over here. Number of sides is 4 minus 2. 4 minus 2 is 2. 2 times 180 is 360. That is the correct number of degrees. So we know that 360 is correct, and we haven't done something horribly wrong, which means we have 21 seconds of error. 21 divided by 4 is 5.25. So we have 5.25 seconds per angle point in our traverse precision right off the bat. So we know we don't have, or presumably don't have, a bad busted angle. Now we take this and we'll adjust the angles by subtracting. So we came out over 5.25 seconds per angle. So we will subtract 5.25 from each of our observed angle rights. And here we go, 79, 54, 50 minus 5 is 79, 54, 45. Now, if we're just going to the nearest second, I mean, you could have made this 44.75 degrees, but really 1 second of arc on especially something this small is negligible, so we just round. But now we've got to get it to 21, so what I've decided to do is add back 5, 5, 5, and 6. That's 21, and then that will sum us out. So we add the most at the least, at the last. So all of these observed angles, 21 goes down to 16, 58 goes down to 53, and then 21 goes down the full 21 to be 76.40.06. As a check, because everything we do in surveying, you can check it and know that you're right. We add the adjusted angles, they come out to 360 flat, so now we're good. Now we're going to take these adjusted angles and compute our azimuths around our figure. Now you can do this any number of ways, but visualizing it with a sketch is the best way in my opinion. So taking our back azimuth of 185 adding 79, 54, 45, our adjusted angle, we get a forward azimuth 2 to 3 of 264 degrees, 54 minutes, and 45 seconds. Now, if you'll remember, I said we're only going to take one distance, and that's forward. So that's what we're going to do right here is we're going to reduce this slope distance to horizontal distance. So it'll be 89, 45, 35. Convert that to decimal hours, take the sign, multiply that times the distance of 137.70. Comes out to 137.699. And we'll carry our values out to 3 decimal places so that we don't really lose anything appreciable in the rounding. We take the 264, 54, 45, take 80 off of that, that's 84. 54, 45 is our back azimuth. Add 89, 49, 16 to it, and you get 174, 4401 as your forward azimuth from 3 to 4. Reduce the slope distance to horizontal. Boom, there it is. Rinse and repeat till you get around. And if you'll, we get a check, just like I said, everything that you check, everything that we do in surveying has a check. Forward azimuth of 108, 1954 from 4 to 1. Add 180 to that, it's 288, 1954. Add our adjusted angle of 76, 40.06, and that will come out to 365 degrees. Anytime you wrap around 360, you take 360 off, so that comes out to 50000, which means we have adjusted our angles and computed our azimuths correctly. That's how you check that. So that's everything that we need from the field notes to take it to the next slide, which is closure computations. So the book in table 10.6, which we talked about in the lecture, gives a format. One thing I don't like about it, it goes XY or east-north, whereas surveyors go northeast. And they say departure latitude, I say latitude departure. So as long as you know what you're doing, it's okay. Here's what we've done. And if you want to refer back to the field book, print it out or look at it on a different screen or whatever. We're starting at 2, and we're just having assumed coordinates of 5,000, 5,000. And we've talked about that before. That's just to make sure that you don't get into negative numbers. If you thought you were going to be traversing a mile in a westward or southern direction, you might bump that up to 10,000, 10,000. But this way you never have any negative numbers in your final coordinate value. And I just broke this up in a tabular fashion. You can certainly do this with a spreadsheet or with a Word doc, as long as you're computing this with your calculator and entering the value so that you see what happens. Truly, ladies and gentlemen, in my opinion, this is the only way, what we're about to do, to visualize how coordinates come to life, or as I say on the title of the slide, how to make coordinates, like DIY. So from here, we're starting out at 2. 5,000, 5,000, but before we get there, we load in all of our data, our horizontal distance, our azimuths. And what we've done here, what I've done here below too, is in parentheses, this is like the leg length from the trig level loop. If you remember, we kept track of the leg. So this first distance, 2 to 3, is 137,699. That's the total distance that we have traversed at that point. Once we go from 3 to 4 and add the 174.69, then our sum, we've traversed 312.39. After we go from 4 to 1, we're add another 107, then we're at 419. When we add 220, we're at our total of 640.448. So what we've done here is 137.699 divided by 640.448 is 0.215. So this number in the brackets, this is the percentage of our traverse. That's how we're going to adjust our traverse. At 3 to 4, when we're 3/12, divide 312 and the decimals by 640, you get 0.488. This will make sense in a minute. But for now, look at this and realize that what we're doing to determine the latitude, the delta north. Notice I've added in here to try to keep it straight. The latitude is the delta north. So you take the cosine. Remember, this is cosine and sine. So the cosine of 264, 54, 45, multiply that times 137.699. Don't forget to convert your angles to decimals. Comes up with a value of negative 12.211. Now look back at our chart. We've got a 264 azimuth. That's about 5 degrees or 6 degrees below due west. And so yeah, we're actually lowering as we go. So a negative latitude is appropriate. Take 264, 54, 45, convert it to decimal hours. Take the sine, multiply that times 137.699, and you get a negative 137.157. Well, look at our azimuth. We're going nearly west, so our east value, or our x value, is going to decrease. Just imagine coordinates on our field sketch, and you'll see this makes sense. So our northern sub 1, I'm just calling it sub 1 because that's our first time. That's our preliminary coordinate. I believe the book calls it preliminary coordinates. I just call it N sub 1 for first draft. And then over here the correction goes, I've got it in the same line, but I'm using it underneath it, but we're coming back to that. So I take 5,000, 5,000, so my north value, I take 12.211 off, and I come up with 4987.789. Take 5,000 east, subtract my 137.157, I get 4862.843. Now I take these coordinates and I do this value. I take my 4987.789, subtract my latitude from 3 to 4 off of that, which is negative 173.954. Refer back, we're going almost south. Just 5 degrees off of due south, so we're taking a big negative decrease in our north value, but we are sliding, we are slightly southeast, so our east value is actually increasing. And the nice thing is, you just take these azimuths, sine and cosine. You don't have to worry about converting to bearings or anything, and it gives you the correct value because that's how trig works. So this gives us the new north 1 and east 1 of number 3. Rinse and repeat. Compute the latitude, compute the departure. Compute the latitude, compute the departure. Take this value off of that, add this value because it's positive to that, and you wind up with our computed ending coordinates of 5,000.007 north and east value of 4999.971 east. So, but before we get there, you may remember how in differential leveling we added and subtracted the four sides and they should zero out. What they don't zero out is our error. Well, we're working in the other two dimensions now. That was the z value. This is the n and the e. So I take our latitudes and sum them. They sum to 0.007. We come up a little bit high. We come up 7 thousandths above 0. We take our departures and add them up. We wind up with a negative 0.029. Now this is just simply, the two sides of a right triangle. Our north value is 0.07. I really should have drawn that up here like this. Our east value is 0.029. Pythagorean tells us that the error, the hypotenuse, the actual distance between these two ending coordinates is 0.03 or 0.030. And you actually divide 640.448 into that number. I've actually got it drawn wrong. But you divide 640.448 divided by 0.03, and that gives you your error of closure, which is 1 part in 21,348. You can say 1 feet or 1 foot in 21,348 feet. You can say 1 inch, 1 meter, whatever. It's still a mathematical ratio. You divide it. If you divide it, the actual ratio is what your error is, which is 0.3 divided by 640.448. That's like 4.68 to the negative fifth power, because that's a bunch of zeros. But you take the inverse of that, divide 640.448 divided by 0.03, and there's your 21,348. And we know from our field notes where we added our angles, our n minus 2 times 180, that we've got 5.25 seconds per angle point. So this is critical because when you perform a boundary survey using a total station or a robot, any kind of direct measurement, direct observation measurement approach as opposed to GPS, you're required to report your error of closure and your seconds per angle point if you have a closed traverse. And so here we are. This is how you get 5 seconds per angle point, 1 in 21,348. So now we're going to adjust this out. So our latitude, our north error, is a positive 0.07, so we need to take off incrementally from our preliminary values until we get that. So we take our accumulated length of the traverse of 0.215. That's our ratio of how far into the traverse we are going from 2 to 3. So we'll take 0.215 times 0.007, because we're adjusting the north, and that gives us this. Let me change color. Negative 0.002. Again, that is our portion of the traverse leg, 0.215, times our north error, which was 7 thousandths of a foot, gives us 2 thousandths of a foot. Next time around, from 3 to 4, we're 0.488 of the way by. So multiply that times 0.07, and that's 0.03. I find it easier to adjust northings and then eastings rather than adjust northing and easting. Just like I find it easier to compute all of my latitudes at once and then come back and compute all of my departures at once, because it's the same function, same strokes on the calculator. When you try to do it one step at a time horizontally, you're liable to make some errors. From here, from 4 to 1, we're 0.655 of the way into the traverse, so we multiply that times 0.007 and get 0.005 for our adjustment, or our correction. And then here at the last one, we're closing back in. We're one full whole value of our error is going into this. So the whole 0.007 goes into correction on our north sub 1 for our check. So we take you do the same thing for the east. So you take 0.215 of our easting error, or our departure misclosure, whichever term you like, of 0.029. And since we came out negative in our value, we want to add incrementally back to zero that out. So 0.029 times 0.215 means we're going to use 0.06 positive for our correction. Likewise, we come down here, we're 0.488 of the way in times 0.029. To our second leg, we're adding 0.014, then 0.019, and then 1 times 0.029 is 0.029. So there we are with what we're adding back to it. So we take the correction value for each point, and we add it to our first draft coordinates. 49, so and this is where we get final coordinates. Notice there's no prime. This is just north, and this is just east. So for number 3, 4987.789 minus 0.002 gives us 4987.791. I believe I went backwards on that. That should be 0.787. But luckily I did the rest of them right. The corrected northing for number 3, 4813.835 minus 0.003 gives us 0.832. And so then this is just simple math. And when you come around, again, everything you do in surveying, you can check itself. What we're doing at the same time is we're checking our coordinate value, which means at the end, when we take all these raw computed coordinates through our traverse and we add the adjustment factor around, we come back with our check at 5,000, 5,000, and know that we have computed and adjusted everything correctly. Again, pay attention to your error of closure. If you've done something wrong, you're going to get a very low number. You should be around one in at least 7,000 or 8,000 for the single turn exercise, but you might get lucky, you might go better. So that is how to make coordinates with your professor, Mark Chastain. Thank you.